The debut of 16-row multi-slice CT holds profound implications for the field of radiology. 16 rows for 16 simultaneous slices. How does this differ from conventional 4-row multi-slice CT? Can 16 rows acquire 4 times the range of 4 rows in a single gantry rotation? The answer: no. 16-row multi-slice has the same scan range as conventional 4-row. In other words, 16-row multi-slice subdivides that scan range in order to acquire very thin slices at a rapid speed. But why acquire thin slices at a rapid speed? Wherein lies the diagnostic value of 16-row multi-slice CT? The coronary arteries visualized by the Aquilion. Stent patency. Soft plaque. In the contrast-enhanced region of this coronary artery segment, soft plaque and surrounding walls are clearly articulated. Diagnosis based on such high resolution has never been possible with conventional CT. What new technology has enabled this quantum advance in imaging capability? The CT screen has 512 by 512 matrix composition. The scan field of the heart is about 250 millimeters, so 1 pixel is equivalent to 0.5 millimeters. This XY plane is the basis of resolution in the axial plane. Sagittal and coronal resolution are determined by the slice thickness in the Z, or axial direction. If that slice thickness can be reduced to a ½ millimeter, the X, Y, and Z directions will become equal or isotropic. If volume data is isotropic, diagnosis can be performed using sagittal, coronal, or axial images with equivalent resolution. That's not all. Isotropic imaging means 3D imaging with no distortion. A 3D CT angiographic image visualized by the Aquilion. The image is distortion-free, viewed from any direction. The bleb of an aneurysm is clearly defined. Not only the AICA and the PICA, but also its thick, penetrating branches are depicted. This image, too, was reconstructed from isotropic data acquired using a thin ½ millimeter slice. This is not a plain radiographic image. This, too, is an image visualized by the Aquilion using a ½ millimeter slice. In the field of orthopedics, multi-slice CT is being tested as an alternative to plain radiographic imaging. The early arterial phase in the abdomen. High-definition 3D imaging on a par with angiography. This was also acquired using a ½ millimeter slice. The multi-slice scan using contiguous thin slices is fundamentally changing the concept of CT. Thin slice isotropic volume data acquired at high speed permit CT to replace angiography or plain radiography. This is the current trend in CT diagnosis. thin slice acquisition for images of the highest resolution. Incredible speed and accuracy. Right now, these performance capabilities are the focus of competition among the leading manufacturers of 16-row CT scanners. Here are the three types of detectors currently used for 16-row multislice. First, the Aquilion detector. 16 rows of 0.5 mm slice detectors in the center and 12 rows of 1 mm slice detectors on either side. A total of 40 rows for data acquisition. Next, Maker A's detector. 16 rows of 0.625 mm slice detectors in the center and 4 rows of 1.25 mm slice detectors on either side for a total of 24 rows. Finally, the detectors of makers B and C. 16 rows of 0.75 mm slice detectors in the center and 4 rows of 1.5 mm slice detectors on either side, also for a total of 24 rows. Three kinds of detector: 0.5 mm, 0.625 mm, and 0.75 mm. What do these differences in slice thickness mean? Although the diagnostic value of the half-millimeter slice is now firmly established and achieving a thinner slice is a common aim, why do these differences, even now, persist? One reason is said to be the sheer difficulty of cutting the detector crystal for a half-millimeter slice. But overcoming this difficulty alone wouldn't enable the realization of a half-millimeter slice. This represents the radiation dose of one scan rotation. If the dose of a 1-second 5 mm slice scan is given a value of 100, then the dose of a half-millimeter slice scan would be 10. If the rotation speed is increased to a half-second, it falls to just 5. Hence, the thinner the slice and faster the rotation speed, the more image quality suffers owing to an insufficient dose. To achieve a half-millimeter slice in a half-second scan demands the capability to detect faint photons and reproduce them in a high-quality image. Attempt to do this with conventional CT technology, and naturally, a barrier arises. To overcome this barrier, TOSHIBA set out to redesign every component in the system. To achieve a precise 0.5 mm slice, first it was necessary to generate a sharp X-ray beam with minimum scatter. The Aquilion employs the world's first anode-grounded X-ray tube for CT systems. In conventional X-ray tubes, electrons that strike and recoil from the focus are pulled back into the anode by its positive electrical potential, leading to the generation of X-rays from areas other than the focus. With the anode-grounded tube, the anode potential is 0, so recoil electrons do not return to the anode. With this new tube, TOSHIBA has successfully eliminated extrafocal generation and achieved a precise X-ray beam. Having twice the sensitivity of conventional detectors, TOSHIBA's multi-slice detector detects even faint photons and converts them to a signal of sufficient strength. In conventional sub-second CT, the X-ray beam is detected 900 times, or every 0.4 degrees, during a 0.75 second rotation. Images are reconstructed from these 900 views per rotation. Here the problem arises. afterglow. Strengthening the detector light output to improve image quality results in a longer afterglow. If the afterglow is long, the data acquired will overlap with subsequent data so that image quality suffers. Shortening the afterglow without hurting image quality, another challenge to overcome in achieving the half-second, half-millimeter slice. In order to realize a half-second scan, most manufacturers have simply increased the rotation speed of conventional CT to 0.5 seconds, while employing the same detectors as before. With the increased speed, however, these detectors cannot keep up with the effects of afterglow and ultimately achieve only 700 views. What happens if 900 views falls to 700? This level of image quality makes routine diagnosis quite difficult. In order to maintain 900 views in a half-second scan for routine diagnosis, TOSHIBA newly developed a detector having a short afterglow and also redesigned the data acquisition mechanism. A half-second scan with 900 views. Only the Aquilion can provide such high-level performance. The faint signals produced by the detector must not be obliterated by external noise. TOSHIBA gave the Aquilion's entire gantry a stealth coating to block external electromagnetic radiation. Near-field magnetic field analysis was also performed for each image board, which was then encased in protective shielding so that it wouldn't emit electromagnetic noise. To eliminate friction noise, data from the rotating frame is sent by a non-contact system of optical data transfer, MUDAT. Thorough noise control to prevent noise from mixing with the faint detector signal, another precondition for achieving the half-second, half-millimeter slice. Data acquired using 16 thin slices cannot be reconstructed using the same method as in conventional 4-row systems. In conventional 4-row scanning, data is acquired mainly in the area near the center of rotation, so almost no cone angle effects occur. With 16-row scanning, however, artifacts related to the cone angle multiply in number near the edges of the field of view. Attempting to reconstruct cone-angled data as data coming from directly above, as in the conventional method, will yield poor results. TOSHIBA has therefore employed the Feldkamp method, a reconstruction method said to require the highest computational power. Look at this image. Precisely defined fine lung vascular tissue running continuously up to the subpleural area. Only TOSHIBA's reconstruction method can achieve such true-to-life visualization. Why has TOSHIBA developed such an extremely powerful image reconstruction system? This image is one answer. 3 kinds of 16-row multi-slice CT, but the similarity ends there. Because TOSHIBA 16-row multi-slice is an entirely new kind of diagnostic imaging system that really should be called CVI, Computed Volume Imaging. With this system, TOSHIBA has empowered physicians with a new kind of diagnosis based on isotropic volume data. Moreover, with a single multi-slice scan, CT can now replace plain radiography and angiography and support the simultaneous diagnosis of multiple organs. from CT to computed volume imaging. TOSHIBA 16-row multi-slice has transcended the framework of CT to take leadership in the field of volume imaging.